right, so
It's not VSU.
you'll kind of see I put the next connect assignment up there. So the next connect assignment up there. So as we start kind of working through material, I would kind of start chipping away at that, in the order of which we're going to cover things in class. So we did quite a bit in the future. Don't definitively know now exactly when, but I know that whatever the date that we had our had the exam in the syllabus, it will get moved. So I should have kind of the updated date for you on Friday. I've got some things kind of popped up this month I wasn't expecting, so I'll probably have to have like one class canceled, and I'll probably end up pushing that exam up like one class period. Okay, but I'll mention that on Friday. But you can kind of see that Connect homework will be the only other homework, or sorry, the only other Connect homework before that next exam. I'll also be giving you another Excel assignment, and that'll probably be posted after class Friday. We'll do some Excel work Friday. We might start today, but my guess is not. For sure, Friday we'll kind of tackle that next topic in Excel. Okay. Any questions for me moving forward here? And I think I've got all the iClicker stuff figured out, so we should be good to go moving forward with that. Where did we leave off? I believe we were talking about this guy right here. Okay. So we said, we've got this entire experimental outcome space, and we kind of broke it down into two components. All right. We had what was in events A and B, so the union of those two things, right? And then we knew, I kind of gave you a little bit of insight as to why the shaded blue area is going to be the intersection of the complements. Well, I know that the union can be written as adding up the probability of each event and then subtracting what we double counter, or subtracting out the intersection. So we really have four components that we know we're going to add up to one now. So it's really becomes pretty simple. And once we start dealing with contingency tables, I'll show you how to think about this in another way. But maybe I know three of those and I have to solve for the fourth, right? So really this should be pretty easy algebra. So if I had what's the probability of B here? So sometimes people will look at this, and if you visually try to think about the numbers, it's sometimes kind of difficult to do. So I would suggest writing out that formula that I just set up there, which I'll do on the board in just a second. Because if you look here, the probability of A is 0.5, the probability of intersection is 0.1, the intersection of the complements is 0.3. So what is the probability? So sometimes people will look at this and think, oh, this has got to be 0.5 plus 0.1 plus 0.3. So that's 0.9. The remainder has to be 0.1, right? But the problem is the probability of B includes also this intersection, right? So it's a little bit harder to just kind of visually think about this, but we just write down this equation that we know. We take the probability of A plus the probability of B. Oops, sorry. And then we subtract out the intersection, or what we double counted. This should just represent the union of those two events, right? What's in either one of those circles, either one of those events. We're then going to add in this fourth component, which we said was the intersection of, well, all this space here is everything that's either not in A and it's not in B, right? It's everything outside those circles. So what's not in A complement, and not in B. So from here, it's a matter of plugging things in and a little bit of algebra, right? So the probability of A is 0.5. We're looking for the probability of B. The intersection is 0.1, and then the intersection of the complements is 0.3. Now I just got one equation, one unknown, just a little bit of algebra. So 0.5 plus 0.3 is 0.8, minus 0.1 is 0.7. So we'll subtract 0.7 from both sides. And then we're kind of left with the probability of B there would just be 0.3. Okay. So this equation is kind of where we're starting out. And really all it's saying is if we take everything that's in either one of those circles, right? A union B, A or B, and we add up to everything that's outside those circles, right? Everything that's not in A and not in B, well, that covers every possible outcome. So those things have to add up to 1. And then from there, it's just plugging in what we know and kind of solving for what we don't. Any questions on this before? Pretty straightforward. Huh? So kind of got this here. Oops. Right, and kind of go back and kind of try to reproduce this. And I think I displayed the algebra a little bit different here. Like you could subtract every single number, right, or add every single number each side. I kind of did the math first. I could tell, well, this is all 0.7 and just do it at once. So I'll give you guys a little bit of time to work on this one because I want to kind of give you some practice, but also see kind of where we're at in terms of just being able to understand this concept and kind of do some basic algebra. So got a very similar setup. Leave that up on the board, so that might help. Right, but let's say I told you the probability of event A is now 0.3. The probability of event B is also 0.3. Right, there is some overlap. Right, here's the intersection of this. That's what we're trying to find, the probability of A and B. And then we've got the intersection of the complements. Everything outside those circles, outside those events, is going to be 0.5. Okay. So give you a little bit of time, talk to the people around you, and try to solve for what is the probability of the intersection of those two events. You don't have to be super quiet, like I said. Talk to the people around you, try to make sure you don't understand a part, but maybe they do. Maybe you understand a part that they don't. So
Wait, no, wait, wait, there's no, wait, minus. We have. It would be, oh, yeah. So you have to, so you can only do A plus B plus 6, and then it tells you the 5. So if you add those, so we're trying to find that on that equation. Negative.
not yet.
All right.
We'll do that today. Well, we should get to it today. Actually, pretty soon, right?
It's just that top equation. Okay, so 40. Like so. Minus A plus B 6, yeah, and then 0.5. So 1.1. It's asking for what to subtract.
All right. So if you haven't gotten an answer in, I'm going to close it out here. So if you haven't gotten an answer in, take your best guess. Oh, there should be 14 of us always. Okay. So I'm going to close that out. So we follow the same procedure we just did. We're looking for a different component, but it really should be kind of the same idea. So the only difference is now, I'll leave this one up here. Right? So here was our kind of starting equation, right? We know we took everything that's in these two events, right? You think about this as maybe someone makes more than 50,000 and they're, I don't know, over the age of 40. So there's some people who make over 50,000 and are over the age of 40. There's some people who are, over 40 and don't make over 50. And then everything in the shade of blue would be, well, that's just everyone who makes less than 50,000, but is also less than 40, right? And neither one of those events. Okay. So all we're going to do is we know that that probability of whatever that event A is, so we're told is 0.3. The probability of B is also 0.3. We don't know what the intersection is, right? That's what we're looking for. And then the intersection of the complements, if I was in neither one, whoops, not equal sign. If I was in neither one of those groups, that probability was told to us to be 0.5. Right? From here, it's just a little bit of algebra. Okay. So kind of how you want to do it, but right, I could kind of move this both sides. So that cancels. So 0.3 plus 0.3 plus 0.5 would be 1.1. So I want to subtract 1 from both sides. And I'm left with, oops, the probability of the intersection is just 0.1. Right? Yeah.
Just for a refresher, so
Mhm.
the probability of A plus B minus the intersection of both is the union.
Yep, that should just be our union, right? That's the probability that I'm in either one of these circles. I could be just an A, just an B, or it could be in both, right? But it has to be in one of them. Okay. Any questions on that? Everybody got it right, so no questions? Okay with this? Okay. So it shouldn't be too bad. Let's see where we're at. Everybody did get it right. Oh, yeah, shouldn't have wasted so much time, right? So I've kind of got a slide that's kind of working through there. So you can always go back and kind of, as we're getting closer to exam, kind of look at these questions, make sure we know how to do it. So the next thing that we're going to talk about is this multiplication rule. So I'll try to give you some insight as to what's going on here. But you could also, if you really wanted to, just memorize the rule. So let's say we've got the intersection of two events. Right? I can actually solve for that if I take a conditional probability and I multiply by whatever event I'm conditional on. So I introduced the idea of conditional probabilities last class, but here we're thinking about if I've got a conditional probability, it's whatever's on the right-hand side of that line. That's what I know has occurred. So given that I know A has occurred, what's the probability now that B occurs? So we call this the conditional probability of B. So just to get a little bit of an insight here. So we would call this the kind of unconditional probability of event A. And then here, this is the, oh, sorry, I wrote this. Do this, but show you this idea. So this is the conditional probability of A, right? So I'm still looking for the probability of A. Whatever's on the left-hand side of that conditional line, that's what I'm looking for the probability of. But I'm now told that this other event B has occurred. All right, so this is the conditional probability of A. It's the probability of A conditioned on that B has already occurred. So this is the idea of me slipping and falling, right? I know, that probability greatly increases if I'm given this other event, which is that it's freezing rain for the last hour. Okay. So I know that kind of this conditional probability can be altered by having this additional knowledge. So let me try to give you an insight as to why. So let's think about, it's the easiest way I can do this. Okay. So I'm not going to use circles here, but this is still my experimental outcome space. I think rectangles would might make this a little more sense, right? So this entire space on the right-hand side, I'll call event A. Okay. I'm gonna do a really extreme example to make the point, all right? So the probability of A, try to draw this so that it exactly split my experimental outcome space in half. All right. So maybe this is something like 50% of the population is over the age of 45, 50% is under. Right? Some event that's exactly splits it in half. I'm then going to think about this rectangle down here is event B. So maybe to help make this make sense, right? The entire half over here is A, but then only half of that space is event B. Right. So if I'm thinking about the unconditional probability of B, try to draw this so that it's split half and half. So the probability of B should be what? Yeah, just a quarter, right? Or the probability would be 0.25. Okay. But if I think about what's the conditional probability here, so maybe I want to know what's the probability of B, given that I know A has already occurred. Okay. Well, if I'm told now that A has already occurred, I know basically I have to see an outcome somewhere here. Now, I don't know which outcome it is, but I know it's somewhere in this space. So now that I know that A has occurred, the entire experimental outcome space is 1, it's almost like my denominator is now only, or anything with this way. I can think about my denominator here would now be like half, right? The amount of space I'm left with is no longer 1, it's just half of that, 0.5. Okay? So you kind of think about here, given that A has occurred, well, I know of that space of 0.5, how much of it is in event B? 0.25, right? If you tell me that A has occurred, well, I now know that there's actually a 50% chance that I'm also in event B, or the probability that B occurs with its additional information has risen to 0.5. Okay. Any questions on that? Does that kind of make sense? So it's basically like, once I know this other event has occurred, I'm limiting the space I'm looking at. So my denominator is no longer 1, it's whatever the probability of that event is itself. Now I've got this rearranged a little bit up here. So how do we end up getting this multiplication rule? Well, what I was really doing here was, what did this 0.5 represent? Well, that was just whatever event I was told has occurred, or whatever I was given, that's my new denominator. And then what was this up here? Well, this is of the remaining space, space A, event A, how much of it overlaps with event B? Well, overlaps, we should kind of be thinking already, this is the intersection. All right. So I've really got the conditional probability is the intersection of those two events divided by whatever I'm conditioning on. So this multiplication rule, I think I have a thing here, maybe this goes, there we go. All I'm really doing to get that multiplication rule is taking what we just discussed and just, oops. Oh, I worked backwards, sorry. So this is, I think, the easier way to understand it. All I'm going to do here is just rearrange it where I multiply both sides by the denominator. And that's where that multiplication rule is coming from, right? So the conditional probability times what I'm conditioning on will give me the intersection. Or said differently, if I want the conditional probability, that is the intersection divided by what I'm conditioning on, right? And it's rearranging that equation a little bit. If that's not quite clear, I can write it up here. Maybe do the algebra and kind of show it to you. So if I've got, what do I want first? A is the probability of B given A times the probability of X. Right? I could just rearrange this where I divide both sides by the probability of A. This cancels. Now I'm left with the conditional probability is the intersection of these two events divided by the probability of what I'm conditioning on. Right? And I think this intuitively makes more sense because you could kind of see the visual there. Like once I know my new space is not the entire experimental outcome space of 1, it's a much smaller area. Well, then that's my new denominator. Any questions here? So, this works either way, right? So if I want to be conditional probability of B, right? The probability of B conditioned on A. Well, that's the intersection of these two events divided by what I'm conditioning on, right? What I'm conditioning on is what's on the right-hand side of that vertical line. Kind of similar if I want the conditional probability of A, that's the intersection of the two events. Now I'm conditioning on B, so I divide by the probability of B. I divide by whatever I'm conditioning on. Because whatever I'm conditioning on, that's telling me my new space, right? My new area of outcomes that's left. So this is just kind of a summary slide. We've now went through kind of the complement rule, there's addition rule. I'm even to push this a little bit further, right? It's not just that we can solve for the union of two events. We had kind of the union plus the intersection of the complements is equal to 1. And then now we've got our multiplication, right? So what does this look like when we actually go to a contingency table, right? That we can build from an actual data set. So I call this R1, C2, you can call this A complement, B complement, just giving you different events so we can think about it. It doesn't matter how we label these things. I think I gave you one problem on the Connect, which I won't ask you to do something like this on the exam. Sometimes on the Connect, I'll push you a little bit further. It could be that you don't just have like event A and A complement, it could be that there's like 4 different outcomes. So you can imagine, like, instead of saying something like, what's the probability somebody makes more than 50,000 and then complement less than or equal to 50,000? Maybe you break it up into 4 categories. So maybe there's a probability someone makes between 0 and 25,000, 25 and 50, 50 and 75, above 75, right? So you would still have it like cover every possible outcome. You've just broken it down into more events. So you could actually have a contingency table that had like 4 columns here, 5 columns. But for now, we'll kind of keep it at 2. We'll keep it simple. I'll show you an example of it later on. Today, I'll keep this simple. So if I want the conditional probability here, I can use this multiplication rule. Now, I have it written up here in a general context of events A and B, right? So if I'm looking for the probability now of R1 given C2, how could I rewrite this? Because everything in this contingency table, right? The totals represent the probability of the events themselves. And in those top 4 left cells, I said all represent intersections of whatever the row and column is. So there's no conditional probabilities directly on this contingency table. But how could I rewrite this conditional probability? It should be the intersection of those 2 events. So the intersection of those 2 things. And then I divide by whatever I'm conditioning on. Well, what am I conditioning on here? The event of C2. Well, now I can get these from the table. What's the intersection of R1 and C2? The probability I see that is R1, C2. That probability is 0.2. What's the probability that C2 occurs? Go down to that total, 0.5. Right? So I can get these conditional probabilities from my contingency table. It just takes a little bit more work. Okay. And like I said, I'll put some actual names to these when we start work when we look at Excel. And I think this becomes a little bit more interesting. We can do a little bit more interesting things and other just like R1, C2, right? Any questions on this one before we keep going? No. All right. So, well, I'll give you guys a little time to work on this one, and I'll kind of ask you. So, instead, what if I asked you for the probability of this? Okay. So I want to know what's the probability of C2 given R2, right? So give you a minute or two, work with the people around you, try to come up with kind of how you would solve for this. And hopefully at the end of the next 2 minutes, you guys will have the correct answer. Maybe even a little bit less than 2 minutes, but I want to give you guys some opportunities to kind of work on these, figure out what problems you might have in tackling these problems on your own. So instead of what we just found, I want you to try to find the probability of C2 and R2, or sorry, C2 given R2. Talk to people around you. Don't be quiet. This is the time to get some practice. Yes. Yeah. All right. So where do I start out here? If I want a conditional probability, how can I rewrite that? Yeah, so C2 and R2, what's the probability that I'm in both of those events? I then divide that by what? I divide that by the probability of whatever I'm conditioning on, because once I condition on it, that's my new space. So here, what's the probability of Let's start with the easy one. What's the probability of R2? Go to R2, go over to the total column. So you know the kind of space we're left with is 0.4. What's the probability we see the intersection of C2 and R2? 0.3. So that conditional probability would be 0.75. And you kind of think about it, we're looking at this table. So once I know that R2 has occurred, it's basically like, well, if R2 has occurred, then I can only ever see R2 and C1 or R2 and C2. Those are the only two possible outcomes, right? If these two events are like filling out the entire experimental space. So of the remaining 0.4, 0.3 of it is in C2, right? Or 0.3 out of that space of 0.4 is in C2. So that makes my conditional probability 0.75 there. You can kind of think about what if I wanted to do the probability of, this should be pretty easy actually, C1 given R2. Well, I'm still conditioning on the same thing. So what space am I left with still? 0.4. Of that space, how much is in C1? 0.1. 0.1 over 0.4 is 0.25. Right? Kind of leading you into something we'll be talking about down the road, which is Bayes' theorem. But the idea is when I'm conditioning on the same thing, well, if I've got two events that are like complements, or they fill out the entire space, right? C1 plus C2 is the entire space of 1. Then I know that those two conditional probabilities would always have to add up to 1, right? When I take the probability of C2 given R2, and then I add to that the probability of C1 given R2, well, that fills up the entire experimental space that I was left with at 0.4. We'll go over that in more detail down the road because it has some extra uses for us knowing that, but kind of just showing you some stuff today to kind of promise for some future topics. But we should know how to calculate these conditional probabilities. Okay. So independent events. There we go. So we say two events are independent if the conditional probability of the event is the same as the unconditional. So if the unconditional probability of A is the same as the conditional probability of A, right? A conditional on B, we still those are independent. Because what that's really saying is the probability of A, it doesn't matter if I know event B has occurred at all or not. Right? So this would be the idea of like if I say, what's the, if I define event A as me slipping and falling, right? And then event B is I tell you that so let's say I'm slipping and falling right now, right? That's my event A. I then give you this additional piece of information, event B, which is snowing outside. Who cares? I'm thinking about the probability of me slipping and falling in this class right now. It doesn't matter what's going on outside, right? So knowing that it's out raining or snowing outside doesn't change the probability that I'm slipping and falling right now inside at all. Those two things are independent. There's no relationship, right? Knowing that one has occurred, well, it doesn't impact the likelihood that the other event happens. So that's the idea of an independent event, but we can check to see whether things are independent using that contingency table, right? Because we just showed we can calculate these conditional probabilities, and it's very easy to get just the probability of the event itself from that table, right? So one nice thing is, I'll walk through it before I walk through on the slides, because I think sometimes breaking this down piece by piece helps make a little more sense, okay? So usually, we say that if I just rearrange this our multiplication rule that we started out with was something like this. Right, so I'm just moving that around so that we're solving for the union, or sorry, the intersection of the two events, not solving for the conditional. Well, if events are independent, right, then I know that the conditional probability of B is actually the same as the unconditional probability of B. So if events are independent, our multiplication rule, kind of like when we had mutually exclusive events, it made finding the union easier. If they're independent, makes finding the intersection easier, right? I just have to take the probability of each event and multiply by each other. And that directly comes from this multiplication rule. But when I know they're independent, that conditional probability can just be written as the unconditional probability.
Would it be addition?
Huh?
You said. So find the intersection, wait, hang on. There you go.
So the intersection of two events, right? If I want to know the probability that A occurs and B occurs. If they're independent events, I can simply find the intersection by multiplying the probability of the events themselves. Okay? So give you a little bit of an idea, or maybe a toy example. So let's say I'm flipping a coin. I'm kind of ruining something I have later on, but that's okay. Say I flip a coin. What's the probability to get a heads on the first flip? I'm not trying to trick you. Right? If I flip a coin, the probability to get a heads is 0.5. Right? What's the probability that I see a heads, and we'll call this on the first flip, on the second flip? Still 0.5. Right? What's the probability I see a heads on the first flip and a heads on the second? Well, each coin flip is independent from each other. If I flip a coin and it comes up heads 4 times in a row, what's the probability on the fifth coin that comes up heads? Still 0.5, still 50%, right? Each flip is independent. So to find the probability I get a heads on the first and the second coin flip, if they're independent, I should just be able to take the probability of each event, multiply it by each other. So here that would be what? 0.5 times 0.5 is 0.25, which we kind of looked at this when I was talking about classically assigning probabilities, right? If I flip a coin twice in a row, what are the combinations I can see? Heads, 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 tails, tails, heads, tails, tails. There's 4 possible outcomes. That one intuitively kind of know, okay, so then to get to 2 heads, I have a 1/4 probability, but I can actually reproduce that using this idea of independent events, making that multiplication a little bit easier. And that's more interesting if you want to do things. Well, I've got an example, or we'll get to something more interesting here in a bit for independent events. But that's the kind of idea. Does that help clarify it a little bit? Is that? So we already talked about this, right? It simplifies this down, kind of broke it down a little bit step by step on the board just to make that look a little bit easier. So let's look at an actual contingency table and see if we can prove that 2 events are independent, right? And I think the example that we'll use in Excel, I can never decide what I want to do because I've got homework, so I've got examples I want to show you. I've got some COVID and county level data, but I think I'm interested. I think we're going to look at average incomes in counties and see how that's the intersections and the unions with the percent of the county that got vaccinated to see if there's like some relationship between income levels and the decision to get kind of a COVID vaccine. So these events will become more interesting. But for now, if we can build a contingency table from data, we want to be able to use that contingency table to prove if these events are independent, right? Does the income in a county change the probability of them having above a certain percent of their population vaccinated at all? If it doesn't, it might be interesting to some people, might break some stereotypes. I don't know yet. I haven't actually done it. I've got the data sitting there. We'll kind of find out together. Okay. So how can we find out if they're independent? Well, we know that the definition of independence is that the unconditional and the conditional probability of the same event, right? Event A are equal to each other. So here, what's the probability of A? 0.6, right? We can break this down a little bit. So I've got, this is my definition of independence. We just said the probability of A is 0.6. Well, the problem is I can't get a conditional probability directly from the table, but what can I do? I can rewrite this as the intersection of those 2 events divided by whatever I'm conditioning on. Okay. Well, now, what's the probability of A and B? No way. Probability of A and B 0.15, right? Those top 4 left cells represent our intersections. What's the probability of just an event B occurring? Go all the way down to the total, 0.25. You can double check me on this, but if you divide 0.15 by 0.25, sure enough, you get 0.6. That equality holds. So we say these 2 events are independent. Right? If for some reason they weren't the same, where's my, if for some reason they weren't the same, or we had that they were unequal, well, then we would say that they're not independent, right? They do depend on each other. So you could work through this one, right? We just kind of had this in the board. You could also work the other way, right? You can actually work to show that if A and B are independent, you can check it by seeing if the unconditional and the conditional probability of A are the same. You could also check to see if the conditional probability of B was the same as the unconditional probability of B. So if I go ahead and do that, I find that the conditional probability of B is 0.25. Sure enough, the unconditional probability of B is 0.25 as well, right? So it doesn't matter which way I check it. I can check to see, does the probability of A equal the probability of A given B? I could also check to see if the probability of B is the same as the probability of B given A. Doesn't matter which one I check, they'll both either tell me they're independent or they both won't. Okay. Any questions here before I go one step further? So there's 2 ways you could check it, right? Either one, you only have to do one, you don't have to do both every single time, right? The other one that's kind of, I think, easier, because like this one, I've got to think, okay, I got to rewrite my conditional, intersection, pull multiple things. Well, one thing that we said we know is true is that if they are independent, we said we could get the intersection of the 2 events by simply multiplying each probability by itself. So here I could say, well, what's the intersection of A and B? 0.15. What's the probability of A? 0.6. What's the probability of B? 0.25. This ends up being the same thing. So if that equality holds, that shows me they're independent as well, right? So there's 3 different ways really to check this, right? So I can go ahead and figure out 0.25 is 0.6 is also 0.15. There's always going to be 3 different ways from your contingency table you can check independence. So any questions on that before we keep moving here? Okay with this for right now? Now, I won't expect you to know this like on the exam, but a really interesting byproduct, and you can walk through the mathematical proof. It's not very interesting, but if 2 events are independent, what has to be true is that their complements are independent as well, right? So if the complements are independent, it means that the intersection of complements should just be, probably each complement multiplied by each other, right? So we can actually prove this with this contingency table. Well, I guess I'm showing you this. Say if you have to believe me that it would work for any contingency table, right? Or Google the mathematical proof. But we see here, what's the probability of the intersection of the complements? 0.3. If I then take the probability of A complement, 0.4, times the probability of B complement, 0.75, or getting your calculator, 0.75 times 0.4 ends up being 0.3. Right? So if 2 events are independent, their complements end up being independent as well. And it's kind of makes sense. So if 2 things were unrelated, so let's say I want to know if someone's over 6 foot tall, and the probability that, I don't know, they something that would be unrelated to, that they have make over a certain amount of money. Now there might be a relationship between height and income. There's like some research suggesting maybe, but let's assume like it shouldn't have any impact, right? So the probability that you're over 6 foot tall and then you make more than $100,000, if those are independent events, knowing that you're over 6 foot tall doesn't tell me whether or not, anything about whether or not you'll be able to make more than $100,000. Well, then also the complements of those should be independent. So the fact that you're less than 6 feet tall shouldn't tell me that you make less than $100,000, right? So that's kind of an idea of, you know, you got two independent events, those complements will be independent as well, right? You can kind of think about independence as like these two things aren't correlated. It's not quite the same, but it's a general idea. Okay. Any questions on that before we keep moving? So, I don't know, I found this and I thought this was an interesting thing, right? The probability of getting a 3 with one throw is 1/6, but the probability of getting 3 with a double throw, right? The two dice add up to 3. Well, there's actually only one possible way you can do that, to get a 1 and a 2. So the probability you actually get a 3 by throwing your dice twice, then it falls all the way down to 1/6. And what are you doing there? You're really just saying, well, look, the probability that I get, you know, roll a dice and I get a 1, it's probably 1/6. Then on the next roll, I have to get a 2 in order for the sum to be 3. So the probability I get a 2 on the next roll is 1/6. So the probability if I roll a dice twice in a row, that I end up getting a total of 3, 1/6 times 1/6, actually falls all the way down to 136. So I don't know, maybe this is like elevator talk or I don't know, small talk that can amaze people how smart you are, right? But the next thing that we're going to do, and I'll kind of start it today, and then we'll finish it up on Friday, is this Excel example. So I put this up on Canvas. Let's double check that I'm not lying to you. I believe I did that before we started class today. So I've got this county COVID data sitting up there, right? And we'll start looking at it and figuring out, can we build our own contingency table? So put this here this morning. Why am I not seeing it? I can download it. So we'll open this up. We've got all this data here. Okay, whatever. So let me get rid of this. Let me change the view. All right. And this is just kind of more like data practices, like best practices. So what I'm going to do is go all the way over to this very top left cell. I'm going to hold Control Shift, hit the over, then the down arrow. I'm going to copy it. There we go. And then I'm going to paste it on a different sheet. So I just went down here. I clicked on this add button that adds a different worksheet. I'm then going to paste it. You don't have to do this if you don't want to. I'm just going to do it because with the view, it makes it a little bit easier to show you this. We're really only going to be concerned with two variables here. So I'm going to look at median household income and then the percent of the county that's vaccinated. So I keep my original data here on this first sheet, but over here, I'm just going to delete the variables that I don't need for this example, just so it makes it easier for us to see everything. So I've got my percent vaccinated and my household variable here. I'm going to delete these because we don't need them either. Now, when I zoom in for you guys, makes it a little bit more manageable, right? What did I delete everything but? Household income and percent vaccinated, right? You don't have to do this. You can use those two columns if it's easier for on your laptop. But generally, if you know that you're only going to be working with two variables, keep the original data, right, on its own sheet, and then just copy and paste it and keep only the ones that you want to do. Yeah.
Like, if you delete everything, how do you put them all in the middle, like close the gaps and stuff?
So, okay, so I'll show you one more time. Okay, so if I Control Shift, Command Shift on Mac, hit the over and the down arrow, I then copy and paste this on a different sheet, right? Probably the easiest way to delete things is going to be to select up here the entire column. So notice if I click and then drag all the way over here, I didn't need any of this. I could then right click and then hit delete, and it'll automatically delete those. Now, if you didn't do that and you just hit the delete button, well, now how do I move things? I select the column I want to move. Notice I've got like this four-sided arrow. I can then move it over. Okay. So kind of two ways of doing that, right? If I hit the delete button, it'll leave these blank columns. If I want to delete the columns, then I just click up here on the column headings. Now, if I right click and hit delete, it'll delete all that blank space for me as well. Any other issues or questions on that? So if you want to delete columns, I think probably the easiest way is just to go up here, select the ones you want to delete, then right click and hit delete. If you just hit the delete button, it leaves the space blank, right? But when you right click and hit delete, it gets rid of the columns for you. Okay. Any other questions on that? Like I'm seeing some confused looks. We're good? Okay, so if you go up to these names, right? What variables did I want to keep? I said I wanted to keep this percent vaccinated, and I wanted to keep this median household income. I will then literally go through and just select all these other columns that I don't want to keep. I can do this in parts. I could do this, you know, kind of breaking it down here. We didn't want to keep any of this. If you really want to, you can just leave these two. I left the county names on the other one just so we have like a reference. Okay? Might be interesting to kind of see that. Okay. But really, for what we're going to do, we just need these last two columns, or the two columns that we're left with. Sorry. All right. Good questions on this? So I'm then going to set up my contingency table. Okay. So to get a general idea, right, to maybe what might be interesting is I'm going to think about maybe counties that have above average income and counties that have above average vaccination rates, right? So just to get an idea, I'm going to find the mean of these two things just to kind of have a nice little reference for what might be a high vaccination percentage in my county. So I'm just going to use that average function and select that vaccinated column. And then I'm also going to think about, well, what might be higher than average incomes? Well, I'm just going to find the mean of income as well. So, right, this kind of, these don't have to be my cutoffs, right? But I'm going to use them for my cutoffs initially. So what I'm going to say down here in my contingency table is my first event is above average income, right? And then what would the complement, sorry. So if I have above average income, this gets a little bit weird, but what would my complement be, right? If this is my event A, what would a complement be? Below average, I have to be a little bit more careful though, not just below, but do I have the, you know, less than or equal to, right? So I'm creating those complements. I have to be careful with my equality. So above average income or greater than the average, or not just below, but do I have the average income or below, right? I make sure I include that equality on one of those. Okay. I'm then going to do above average vaccinated. Okay. And then I'm also going to do the complement of that, which would be average vaccination percent or, oops, below. Okay. And I'm going to make those columns wider so you can see what you typed, you double click. So if you're typing this out and, oh no, my words aren't there. If I double click in between, see how I get this like bar with two arrows? If I double click, that widens that column for me. So I've basically now created my event A and A complement and my event B and B complement. So we ran out of time. We've got this set up. What we'll do next class is see how we can use that count ifs formula to actually come up with frequencies for the combination of these events and then turn those frequencies into probabilities. Okay. So we'll pick up on this kind of where we left off next class. I should just save this to my computer so we can kind of go from there. So be ready to work on Excel. I'll then post the Excel assignment after we get through it on Friday. And other than that, we'll see you guys Friday. If you have any questions, kind of as you're working through the Connect homework, feel free to reach out.